Hi, welcome to another lesson at Edu Solutions Institute. Now, today's lesson, we'll be looking at the calculation aspect of last week's lesson, where we looked at energy, power, and work. Now, we're going to do one question that utilizes the principles that we explained on last week's lesson. Now, this question here states that the diagram shows an arrangement used to test golf club heads. The shaft of a club is pivoted and the center of mass of the club head is raised by a height h before being released. After reaching the vertical position, the club head strikes the ball. First part, describe the energy changes that takes place in the club head from the instant the club is released until the club head and the ball separates. Now, the energy changes that will take place here would be, we first would start off with a gravitational potential energy. So at the top, we have some stored energy, so gravitational potential energy. And when it's being released, that energy now will be transferred into kinetic energy, right? Plus heat, because it's going to be rubbing against the the air particles. And then that goes to elastic energy when it's in contact with the ball. Because when the club hits the ball, it's going to compress, right? And then that compressed energy is what will cause the ball to be released. And that therefore goes to kinetic energy afterwards. All right, the next part says calculate the maximum speed of a club head achievable when h is 0.85 meters. So now that we know that the only thing we're given here is the height of release, but we know something about energy, that energy is conserved. So what we can have is that the gravitational potential energy will be converted to kinetic energy. And therefore, we see that the mgh at the top of the flight is equal to the half mv squared at the bottom when it's about to leave the ball. So therefore, we see here that the masses can be cancelled because they're the same mass as the club. Right? Gravitational acceleration is 9.81 times the height, which is 0.85, would be equal to half times velocity squared. And that's what we need to find, the velocity squared. So let's go and calculate. So we now have 9.81 multiplied by 0.85, we get, and then we multiply by 2 to get rid of the half. So we get 16.677 equals v squared. And therefore, to find v, we find the square root of this. So therefore, v would be square root of 60.677, which gives 4.1 meters per second. And that would be the speed where the ball leaves the club on contact. So we notice here we utilize the principle of conservation of energy that says the energy that the object has before would be equal to the energy it has at a specific instant. So before would be when it's at a height of h, and then after is when it's in contact with the ball, when its h is now 0. So therefore, the only energy there is the kinetic moving energy. All right. In the diagram shows the deformation of the golf ball and the club head as they collide during a test. Explain how the increase in deformation of the club head may expected to increase the speed at which the ball releases the club. Ball leaves the club. So we know that the elastic energy increases with deformation, hence more kinetic energy would be converted into. So if we have more elastic energy because we have more deformation, then we're going to convert more of that into more kinetic energy, which would make more speed. All right, so that's all we need to have here, because we know that elastic potential energy is equal to half times kx squared. So if this if this x increases, which is deformation, then that means the potential energy also increases. And if that increases, then that means we have more energy to be converted into kinetic energy. And therefore, if kinetic energy increases, then the speed of the motion will increase. All right, we're coming on good. Next question. Our next part, in a different experimental arrangement, the club head is in contact with the ball for 220 microseconds. The club head has a mass of 0.17 kilograms and the ball has a mass of 0.045 kilograms. At the moment of contact, ball is at rest and the club head is moving with a speed of 38 meters per second. The ball moves off with an initial speed of 68 meters per second. Calculate the average force acting on the ball while the club head is in contact with the ball. So this is from a previous topic that we have done, which is called impulse. And we know that impulse is equal to force times time, or impulse is equal to change in momentum. So we want to know what's the force. So in order to know the force, we would have to find impulse, or we can just combine both equations together. That gives us that change in momentum over time gives us the force. All right. Now, this is the force acting on the ball while the club head is in contact with it. So the club head is providing a force. So we put in the mass of the ball here, which would be 0.045, right? Its final velocity, it leaves with 63, and its initial will be 0. And then the time of contact would be 220 micros, which is 10 to the negative 6. So when we put all of this, 0.045 times 63, and then we divide that by 220 times 10 to the negative 6, we get that there is a force being applied of 12,886.3666, which we round it off to 2 decimal place, we get 13,000 newtons. All right, so that's the amount of force that is being acted on by the club head onto the ball. State the average force acting on the club head while it is in contact with the ball. Right? So therefore, based on Newton's third law, the force on ball would be equal to the force by club or on club. So therefore, that force is equal to negative 13,000 newtons. And it's negative because it's going in the opposite direction, right? So that's all we need to do because it says state, so we don't have to calculate it again, right? Then the final thing is calculate the speed of the club head at the instant that it loses contact with the ball. So this is where we're going to use another principle, which is the conservation of momentum, which tells us that the momentum of the club head times its velocity is equal to the momentum of the ball times its velocity plus the momentum of the club head after. Right? So before, the club had a mass of 0.17. Its velocity was 38. Then it's equal to the mass of the ball, which was 0.045 times its velocity, which was 63, plus 0.17 times VC. Right? Notice that there is no momentum before for the ball because the ball initially was at rest. So therefore, we don't have to include that in the before. So this becomes 6.46, and then we're going to take this multiplication over, which is 0.045 times 63, which we get 2.835 is equal to 0.17 VC. When we minus this, we get 3.625, then we divide by 0.17. So therefore, the velocity of the club would be 21 meters per second. All right, and this would be the velocity of the club after it is in contact with the ball. And notice its speed will decrease because it was at 38. Now it's going to lose some momentum, so it is now at 21 speed. All right, so that's it for today. I hope you understand as we use different principles to apply in the same different concept of energy, work, and power. So that's it for today. I'll see you next week where we continue to learn about the IB physics syllabus. Thank you.